Okay, hope I can keep things in focus here. Cylindrical coordinates. We have the cylindrical coordinate system with coordinates r, theta, z, where r and theta are essentially just polar coordinates in the xy plane. And z is the same as in an XYZ system. The system is often sketched within an XYZ context. And we've already seen how to represent a point in cylindrical coordinates. Let's consider what happens when we hold one of these coordinates constant. Now, in the XYZ plane, holding x or y or z constant gives us a plane parallel to the coordinate plane of the other two axes. That's not the case here. Yeah, for example, if we hold r constant, what do we get? Well, down here in the xy plane, r constant just gives us a circle, and I guess we can extend the x-axis back this way and extend the y-axis over this way so we can sketch the entire circle. It gives us a circle that comes around like this and then around to here. And let's go back here and around to here. There's a circle in the xy plane. So that, to start with, r equals constant gives us a circle. In the xy plane, or our theta plane, whichever way we want to refer to it. Now, z is not addressed. It's arbitrary. So it might be 0, so certainly this circle is part of the region for which r is equal to whatever this constant value is. But z can also be positive, negative, and it can be any place we want. So if we have a point here, we can go above or below that point as far as we like. And we can do the same for any point on the circle, giving us a picture that might look something like this. I'm not terminating these in the vertical direction at any particular distance. Okay, so these segments, and of course there are segments around the back of the circle as well. These segments will represent the set of points that lie above and below this circle. In any plane where z is constant, any plane parallel to our basic r theta or xy plane, we could draw a similar circle, just raising the point up by some fixed amount, which means that if we move up some fixed distance from here and fix that distance for every point of this circle, so that we move up what appears to be a consistent distance. Well, we're going to get something that simply mimics this circle, and we're going to get that at every level, so that we can sketch these contour lines having pretty much the same shape as these, and these are going to continue on up as far as we want to go, giving us a reasonable depiction of this infinite cylinder. It moves on down, it moves on up. It has a back here. I'm not going to try to shade that in or anything. But we conclude that R equals constant is a cylinder its axis is the z-axis. Its radius, well, let's do this, its base is a circle of radius, whatever our constant is, in the r theta plane. So that whereas, again, in the xyz system, letting x or y or z equal constant gives us a plane parallel to one of the coordinate planes, letting r equal constant gives us a cylinder, an infinite cylinder. Kind of wraps a plane around itself. Theta equals constant turns out to, in fact, give us a plane. If we confine ourselves to the xy coordinate plane, we have angle theta here. Now, for any positive r, that's going to give us a point that lies along this plane. As long as z equals 0, we're confining ourselves again to the r theta or xy plane. So if z equals 0, we're going to be on this line, and we could go as far as we wish in this direction. R can also take negative values, so we're going to also come back in this direction. And our plane is going to rise above and below the points of this line. Now I'm going to just draw some portion of this plane, and this time I am going to try to keep these lines of equal length, maintain an equal length with more or less success. So this plane might be represented like so. It's a vertical plane that could be thought of as taking the xy plane and rotating it around through angle theta. The xz plane and rotating it around through angle theta. This plane, of course, extends on down. And up. And we can draw a couple more lines in the parallel to the xy line, the line that we drew in the xy plane. Now it would require a lot more shading to make this look right. This plane intersects, actually cuts the cylinder kind of in half along this angle, and that's not really all that apparent from the way the picture looks. In any case, that's how we would construct that plane we would have to shade this in such a way that lines behind the plane appear to be dotted. In front of the plane, the arcs of the circle of the cylinder would be unshaded, but the lines of the plane that are hidden by that would be dotted, and so forth. The plane z equals constant is, just as in the case of the XYZ system, parallel to your two-dimensional coordinate plane, to the XY or R theta plane. And I'm not going to attempt to sketch that. You can check textbook. You can see lots of good illustrations on the web and so forth that shows this more clearly. We have our transformations between the R theta z and XY z coordinates, where R is the square root of x squared plus y squared. Theta is the inverse tangent of y over x plus pi if x is less than 0. And of course, z is just plain z. So that if we know the x, y, and z coordinates of a point, we can easily find the R theta z coordinates by this transformation. If we have the equation of a surface or a curve or anything in the x, y, z coordinates, we can change it to R theta z coordinates by this transformation. And similarly, if we have the R theta z coordinates, it's easy enough to get the x, y, and z coordinates. X equals R cosine theta, y equals R sine theta, and again, z is just plain z. The volume increment in R theta z coordinates is, as we've shown, just r dr d theta, which is just the area increment down in the polar plane, the R theta plane, multiplied by dz. The advantage, one advantage to cylindrical coordinate system is that it naturally represents cylindrical objects or cylindrical objects intersected with planes parallel to their axis and much more.